later. I misspoke a while back about this when this fellow asked me about why we're putting all that vertex data in there. There was like 72 coordinates in that array of vertices. That was actually a holdover from some older code where we didn't do this indexed. If you actually look at the examples, we're using an indexed method to draw. That's what draw elements does. So what happens is we only have to specify a minimum set of vertices and just continue to reuse them. This minimum set is not the 72 floating points that are in there. It's actually 24 of them for reasons I just don't even want to get into. It would make it harder to do texture coordinates and other stuff if we tried to reuse it for everything. But what we're doing is we're only using 24 of those 72 vertices, and we're using an index array. I'll go take a peek at the code inside here in Eclipse. All right. So what we're actually doing, you were correct in asking this. I was just saying, I misspoke earlier. We're actually not using all those 72 indices. There was a lot of replication in that array that was left over from an earlier example, which I went back and looked at. I was like, well, actually, no, I did do index drawing. So what we're doing is, here's the front face of the cube. It's two triangles, and these are the indices into it. So we're basically getting the first index, well, the 0th, then the first, and then the second to do a triangle. And then we're getting the 0th, the second, and the third of these in an array. So now we built two triangles up that make our quad. And that is used with draw elements, gl.draw elements, as indices into that array of vertices. So I'm actually creating far too many vertices. So I'm going to go clean that up for the next time I do this. And I think that's because I started with a non-indexed cube when I was doing the original examples. So that was a really good catch. And that fellow over there, between what you asked and that fellow over there, he caught it. So be careful with that. And also note, again, I'm actually creating, there's wasted vertices in there. So this is not the best way to do this. So we need to get an updated example. Apologies. And with that, we're going to move into the next section. We're going to try and bang out 2 more sections, maybe 3, depending on length, before lunch, which should be around 12:30. No other lingering questions or issues from the previous? Yeah.
How does the extension map the texture to the cube? Let's say I have, image mapping, right?
Yeah.
I unfold it and then I tell the renderer that this is my image. This is supposed to be here.
Right.
Yeah.
So what's the question?
How does it map it? Let's say
Well, that was the job of the vertex shader, remember? It said, you've given me data that tells me where the vertex positions are. You've also given me data that tells me how those vertex positions are connected to bits in the texture, right? So this piece of the triangle here, let's say it's the top left corner of the front face of the cube, right? That's the 0, 0 position in the texture, which is in a 2D space. That's what those text coord.s and t's are, right? So that's how you do it for every vertex. So if you have some unfolding mesh, those don't change, Once you define those for the triangles and you unfold a mesh, those are going to stay the same, those texture coordinates, unless you want to play games with them to animate them or do something else. Does that answer your question, or are you asking a different question?
Maybe my question is specific. For each face, right, of the cube, I have to supply an image.
No, for each face, that image is reused for each face of the cube.
Okay.
Yeah.
So if let's say I have different images for the different faces of the cube.
If you had a different image for the different faces of the cubes, what you would do is you would supply 6 images to the shader. We supplied 1 image to the shader. What you would do is supply 6 images to the shader along with a variable that was basically an index into which, a value from 0 to 5 that said which texture you're going to use now. And the shader would select that one, which is a completely stupid way to program this because we should be using something like Three.js to do it instead, and it'll do all this for us. But that's how you would do it. That's a great question. Okay, so I don't know about you guys, but I don't want to spend all my time writing shader code and filling up buckets of vertices, and there's just no way to get stuff done on web time. So thankfully, as WebGL started coming out, people were experimenting with it and doing, hey, here's my cool water shader, and look at all these fun effects. Some folks said, well, crap, I can't do this all day long, and started building libraries to go on top of it. And by far the most popular library for doing WebGL development is an open source library called Three.js, created by a fellow named Mr. Doob Never dared ask why. Lives in London now, or maybe he's back in Spain. He's from Barcelona originally. And the folks from Google found him as he was starting to do some demo hack things and creating WebGL content out of a library he'd already been drawing 2D canvas stuff with. So Three.js started as a 2D canvas library. So one of the nice outgrowths of the fact that he ported this from 2D to 3D is he created a system where you can plug in different renderers. So you can render in CSS, 2D canvas, or WebGL, or SVG even. So he got that going, and Google started paying him to do projects, and the Google Data Arts team started building really incredible stuff with it. We'll just look at a couple of quick samples of amazing stuff that's been done with Three.js, and then we'll get into how to use it. I think this has got some sound. Oh, what's up with that? Did I just zoom? Let me hit reload. I must have done something. That's interesting. Give me a second of futz. This should not be happening. One more time. Yeah. There we go. I don't know what that was all about. Never seen that before. So check this out. By the way, remember, still have my 4G tethered through a phone. Yeah, a lot of stuff was in my cache, but we still had to hit the browser to figure out what was in cache. Clear cache. This still loads pretty fast. And this isn't an MPEG, right? This is real-time stuff. I can interact with it. We're seeing all kinds of cool stuff in here. We're seeing a real-time shadow cast below the object. We're seeing environment map reflections. These are not real-time reflections, but they're basically applying extra texture maps to fake chrome surface and reflectivity in a beautifully rendered, fast and furious kind of garage space. Like any self-respecting car app that you see in a web page, they've been built in Flash for years. I can do things like switch the car and switch the colors in real time in my web page. Holy crap. I mean, now we're talking, right? And Three.js gives you the ability to build this without what I would call too much hassle. And we're going to see how. We're not going to build this today. We're going to do the cube again. But it'll take too long to build this. Though in the afternoon, we're going to start building something that's in the spirit of that. Let's see. What else did I want to show? Oh, completely different kind of approach here. What if we want to visualize some data? This is a visualization of small arms traffic around the globe for the last 20 years.
Awesome.
The globe model we're seeing is based on an open source globe project. I think it's on Google Code. I don't remember where it is, but we can go look for it. I can click on a region and see how Russia's been trading arms, for example. Wonder what that looks like in the last 6 months, by the way. I can flick different parts of the UI. I can just look at imports, just look at exports. All right. The US, we're probably no better. We're probably worse. We've got all this glowing shader stuff. We're actually doing multi-pass rendering that makes these glowing effects, and Three.js makes this possible. And again, the wonders of web and open source, all this stuff's freely available to experiment with, hack, cobble, steal, as long as you get proper attribution. So this is the kind of stuff we can build. We can start building some really crazy good apps in WebGL using these technologies. I just want to turn that off. I'm going to do that. Gunk. So let's talk about what it is. First and foremost, you breathe a sigh of relief. It hides all that crap we just looked at in the previous section. So if you want to create a cube in Three.js, you say cube. You don't have to set up all those buffers of data. It's got a lot of pre-built objects, not just canned geometry like cubes and disks and cylinders and toruses and all these sort of platonic solid shapes, but real 3D polygon meshes like we just saw with the car and everything else. Relatively easy to use, especially if you've done any 3D programming before with a high-level toolkit, or if you've tried to build a game in Unity or something. You're familiar with the concepts. You create JavaScript objects and use them. They've done a lot of work on performance. Though this is an open source project that's had a lot of hands in it, I think the performance could be better in a lot of ways. There's other tools out there, other libraries that may start focusing more on performance and all that. And definitely people who are doing high-performance games, they build their own things like this and focus more on performance. But it's overall fast enough for a lot of purposes. Very well maintained. Big team of people helping out with it. It's not just Mr. Doob. There's 4 or 5 active contributors. I've contributed code to it in a couple areas. Supports interaction, so you can know, like, I mean, we haven't even done this yet, but how do you figure out how an object's picked? That's more math. We're going to get into that in a little bit. Gives it to us sort of for free. I don't like the way it's packaged up, so I built more layers on top of Three.js, and we're going to look at those this afternoon for doing picking interaction behaviors. Does all this math for us, that GL matrix kind of math that was in that library. Three.js has that kind of library support for math and more, represented as objects with methods and properties, and pretty easy to use there. Like I'm just saying, it's object-oriented. Very easy to add your own things in subclass, what he's already put in there. And it's got renderers for 2D Canvas, SVG, CSS. So for example, anyone go to those famous talks yesterday? Yeah. Famous, going to rule the world. Yeah, well, I mean, one of the examples they've been touting for years is this periodic table of the elements. You've probably all seen that, at least on TechCrunch or somewhere beautiful. Ricardo, in about a half a day, popped one out in Three.js using his CSS renderer. So you just take CS elements. Each one looks like an entry in the periodic table, map them onto a sphere, and the elements of that sphere are positioned in 3D space. Each element itself is a flat CSS element, and the magic is he's using CSS 3D transforms, which we're going to cover in another section. But you're using all the same APIs, and all you did was say, give me a CSS renderer instead of a WebGL renderer. Very powerful. So especially if you need to do fallbacks like we were talking about, depending on your app. For the Internet Explorer Challenge, or say iOS for now, or I mean, there's lots of reasons you might want to fall back. This is a great way to go. Yeah. I don't think you guys want to try to do this now over this network, but you've got my slides, so you can try to do this later. If you want to browse the Three.js sources, there's so many examples. There's so much, a wealth of stuff in there. You should go get this. You do not need to get it to go through these examples. I've packaged it up with the examples already. It does all that stuff we were doing in raw WebGL. It does it for us. We feed it objects, and it renders them for us. The scene itself is implemented in JavaScript. No DOM objects. Yeah. It's not a DOM. Again, I gave a talk yesterday about how to do a 3D DOM, which is just DOM elements that then talk to 3G. Well, it's complicated. But yeah, under the covers, it's got its own internal representation of what we call a scene graph. We're actually going to cover that in the next section. So you go look through this, go browse it. I most importantly stress, go look at all the examples. There's dozens of them, some canvas rendered, some SVG rendered, tons of WebGL. Shows off all kinds of effects and amazing things that you can do with it. One thing to note here is Ricardo keeps moving, implementing new features. I'm always updating my code to catch up with what he's done. He's up to revision 67 stable of his library. The book examples use, and what we're covering today, use revision 58, because I started working on this book and this project what we're going through today a year ago. And I kind of kept track and kept up for a while, but when it came time to print the book, I had to stop updating the examples. So that library is probably 4 or 5 months out of date at this point. It works with the examples. He's made some changes. Some APIs will be a little bit different. So if you start getting into wanting to be a Three.js jock, I'd be careful about the mismatch between stuff in the book examples and what you'd want to do now. But there are not that many differences, and it's not too bad of a migration, but just a heads up. OK, so now what we're going to do is look at what it would take to do that same tumbling cube in Three.js. Now remember what we were up against before? I think the source code, if you look at example 2-3, was something like 300 lines, right? To make a tumbling cube. I mean, what's the line count in there?
43.
How much?
343.
Yeah. Now if you look at whatever this would be, example what? 3-1? No, Three.js cube. I stopped numbering them and started naming them. Other than the surrounding markup, this is what it takes in Three.js to draw a cube. We had a canvas element, document.getElementById, created canvas, pass it in. We're going to tell Three.js to do anti-aliasing, which is we're going to tell the hardware to do anti-aliasing drawing if it supports it, and what that does is do a multi-sampling drawing technique to get rid of jagged edges you might otherwise see. So we could turn that off in an experiment later and see how bad it looks with that turned off. So we're going to tell that to anti-alias render for us. I don't know why it doesn't do it by default, maybe because it's a performance hit. I would do it by default because it looks better, but anyway. Then we're going to create this scene, which is a hierarchy of objects. So the scene, think of that as the root of a DOM tree. Here's your 3D scene. We're going to put a camera in it. That camera is the same thing as essentially our perspective projection we had before. But in Three.js speak, it's another object in your scene. So for example, if you want to move its position around and animate it, you can move that camera around, and next time you render, your camera's going to be flying through the scene in a different place. Oh, that's happy. Thank you, degrees to radians. You did it for me. But you know, there's a lot of stuff in the Three.js library where you're saying math.py this and that. But at least for the camera, boom. Same thing, aspect ratio. And then I'm going to define front and back clipping planes here. Remember that viewport transformation? This says anything less than 1 unit away from the camera is not going to be drawn. It's going to be clipped. So all your objects better be more than a unit away from where the camera is, because otherwise you won't see them. And this can be an arbitrary value. I'm just saying clip everything here. You've got to define this volume, basically. And this is the back plane of that frustum, that truncated pyramid, which says don't draw anything more than 4,000 units out, right? And under the covers, what this is doing is setting up some low-level WebGL stuff that will take care of all that for you. So this is passed through to the WebGL rendering. I add this camera to the scene, and it's just like any other object. Once it's in there, again, I can move it around, transform it, spin it, and we've got camera animation. I'm going to create a texture map using an image utility in 3, which goes and loads it and does all the magic we saw with the samplers and setting those up and all that. 20 lines of nonsense to get a texture going in 1 line. And then I'm going to create what is called a material. A material defines the surface properties of an object. So remember that 3D mesh of the face? We saw it was also, you know, the vertices were drawn in there, or the quads, but without those things in there, you'd see what the face actually looked like. And you saw there was some shading on it and all that. That's based on light sources in the scene and other things you set up in Three.js. And under the covers, it's all calculated by what's called a material, which really, this is your vertex and fragment shader pair, hidden away from you. And so you don't have to deal with it, and implementing a basic lighting and shading paradigm. In this case, mesh basic material is the simplest material you can use. It's like the material we did in the first example in raw WebGL. It's just taking the pixels out of the texture map and using the UV coordinates from the cube and painting that color. It doesn't use additional colors. It doesn't use any lighting sources, which is why we're going to get to that in a second. We're going to light a cube in Three.js, which is why the cube looks a little funky. You don't see any lighting. You don't see hard edges and all that. So the mesh basic material gives us the pixels. Oh, and how do we create our cube geometry? Remember the lines and lines of setting up the buffer? Yeah, none of that. We say 3.cube geometry. We take the geometry and the material, and we put them together in something called the mesh. A mesh is just another 3D object in the Three.js scene graph. We add it to the scene. So what do we have? We have a scene that's got a cube and a camera looking at it. Everything else from here, when we want to animate, it's going to be really simple. Change properties of the cube. Or you could move the camera around again if you want. Let's see it in action. Question.
Does Three.js fall back to SVG?
You have to tell it. You write your application, you figure out what your browser capabilities are, or you decide ahead of time, hey, I just want to use it because it's a fun library, I know it. I'm going to use it to animate my SVG or my CSS elements. I mean, it's a design choice, but it can also be a fallback choice based on WebGL detection. So you do that code that I showed in the very beginning. You see if WebGL is there. If it's not, you could try to have it canvas render. But you need to understand there's some trade-offs we can look at. Doesn't look as good, doesn't work as fast. It's not perfect. Yeah, but it won't fall back automatically. That's why we have to create it explicitly here. And we say, we want the WebGL version, please. But this assumes that we did the WebGL detect and we knew that our browser supports it, okay? Good question. All right, before we look at the run loop, let's look at it. Oh, no, see, you don't have that one. All right, hang on a second. Three.js cube. I don't have a shortcut to that, so. That's not it. Sorry, wrong Three.js cube. Different talk. There we go, sorry. So I got it rotating on a different axis, a slightly less skewed one. But there it is. Looks pretty much the same. And that's all it took, other than that run loop to spin it around. which got a lot easier as well, kind of. I mean, I'm not using GL matrix anymore. So my run loop, I do the same thing. I do request animation frame. Say, make sure that next time you call me, I'll do run again. I'm going to tell Three.js to render the scene I've supplied it. Remember, it had a couple objects in it, camera and a cube. Render whatever the contents of your scene are from that camera. And so all that stuff about setting up the projection matrices and all that before draw, setting up the buffers, shaders, textures. There are hundreds, if not thousands, of lines of Three.js code that get executed when you say this. I mean, in the case of the cube, it's not that much, but when you're doing a real scene, it goes through a lot of machination. And then we call animate to make sure we tweak the cube next time through. What am I going to do? I'm going to calculate a delta time. I'm going to get a fractional value to convert from milliseconds to seconds. I'm going to derive a new angle from that. And look at this. I don't have to call map4.rotate or anything. I set the y property of the rotation property of the cube, which was a 3D mesh, which was that thing in the Three.js scene graph. And Three.js knows what to do with it. It's going to take that next time through the run loop, it's going to take the new value of y and use that to compute that model view projection in the vertex shader. So we didn't have to. So that's kind of amazing. Everyone get that? I mean, that's really simple stuff. That's pretty intuitive, right? Once you know the API and the syntax, I can take the rotation value of any object, set it's y. I can take a position value of any object, set it's x, y, or z, and move it around in space. It's got a scale component, too. I can take the scale component, stretch it, grow it. Well, that's the way you kind of want to work in 3D, not the way we were doing it before. But, you know, I talked about this already. You may notice the cube's a little funky looking. It's just sort of, there's no hard edges to it or anything. Wouldn't it be nice to light that? It would have been nice to light the stuff, examples from Chapter 2 in raw WebGL, but I don't want to beat a dead horse, but you can imagine that might have been more lines of code and more lines of shader code to compute that lighting, because you have to do that in the shader. More data futzing in buffers, and you know, like I said, I didn't want to beat the dead horse of, yeah, WebGL is hard at its low level. So I didn't light the cube in Chapter 2 at all. But now that we're in this section, let's look at lighting it. What do we need to do? Well, let's look at it on screen first. See the difference? It's beautiful. As the cube moves, I mean, you can see the hard edge on the top of that, right? As the cube's moving around, we can see how the lighting's changing. Let's see how we did it. This is too dark. I don't know if you can see the contrast. So this is Three.js kubelet.html if you want to follow in source. We need to add another object to our scene to light the scene. It's called the light. Hey, that's pretty good. That's pretty intuitive. Three.js has several types of light objects. Simplest one, the fastest one to compute with, but it's maybe not the best one for realistic lighting effects. Easy to just slap some light on a page, though, is called a directional light. A directional light behaves similarly to the light coming from the rays of the sun. It's coming from a direction to another, you know, from one place to another place, but it has no particular position in space. It's just parallel rays of light moving, you know, being cast in a direction. So anything in its path, in that direction that you set up, is lit from that direction. Now, what's interesting is, I don't know where Ricardo picked this syntax, maybe because other lights like spotlights and point lights that we'll get into later have a positional thing. But to set the direction, you set the position of the light, and then it points from that position to a target. And the target by default is the origin. So what we're really saying here is, again, there's no position to a directional light. It's infinitely far away, and it's just casting parallel rays in a direction. So what happens is you set the position to 0, 0, 1. That is, you know, out toward you, and it points to the origin. So effectively, the direction is 0, 0, minus 1. Is that making sense? Because the light's going from out of the screen into the screen. So its direction is negative z, because that's the way negative z goes. So if I was designing this API, I would have said light.direction.set 0, 0, minus 1. Idiosyncrasy of the Three.js API. You get used to that real quick. And then other lights in the system have position, and they have targets. So you have a spotlight, it's here, and it's pointing there, and that means something. And that makes sense, sort of. Makes no sense for this light, but. The second argument after color, thank you. Sorry, didn't mean to gloss over it. So that's a hex color value. It's not RGB here, just because that's the way he designed the API. Under the covers, he converts it to an RGB color. So this is hex, just like your CSS hex would be, 4-component, red, green, blue, alpha. I doubt he uses the alpha in the light at all. And that's an intensity value, where 1 is sort of normal lighting, and that cranks up the intensity a little bit. And it's an arbitrary scale. I can't tell you what units that's in. It's in Three.js light units. And then we have to make one other change to be able to actually see that. Because if you do that with the basic material, there will be no effect. And the shader for the basic material under the covers doesn't use a light source to compute those pixels at all. So what you do is you create something called a mesh Fong material. Fong is named after a human being whose last name is Fong, who did computer graphics research to come up with a high-performance lighting model that could be rendered on reasonable computers. So it's fast, it approximates real-world light, but it's not so realistic that it takes a lot of compute cycles. I mean, there are other more involved lighting models, and you can build them yourself in Three.js as well by customizing shader materials. We'll get into one of those later. But this is a good basic lighting model to show off edges of objects, reflective highlights off the surface of objects, and other things like that. So when you want lighting and you want it to show hard edges and that kind of gradation we saw in the cube, use a Fong material. There's another one called the Lambert material if we have time to go into it, which is great for things like the color shining off the moon. You wouldn't really want to see like pronounced highlights off the edge of the moon. It just luminously reflects everything, sort of diffuse. And that's called the Lambert material. And that was it. We make those 2 changes, and the cube is lit. And those changes do represent a few hundred lines of code in raw WebGL. So we're really up and running and off to the races. So this is a quick section. Wanted you to just get a taste of Three.js. We're going to do a couple of labs. So Three.js cube lit. We're going to just explore syntax here. Right? So how would you use Three.js to make the cube blue instead of white? Leave the texture on it. Don't mess with that. But we're going to see the color underlying it not be white but blue instead. I'm going to pull up the result. That's not it. Wrong one. So it should look like that, just so you know the effect we're going for.
Was the one that we did in raw WebGL anti-alias?
Didn't look very good. I think it was anti-alias, but not texture filtered correctly. Let's go back and futz with that if you care, because it didn't look as good.
Yeah, that's what I was going to say.
And I'm wondering if I've got some bits flipped in the code just because I've been messing with this stuff before the lesson. So I noticed that too. I was like, maybe over the lunch break we'll take a quick look, so we'll follow up on that. Because the cube edges were kind of okay, but it was more like the quality of the texture filtering. Yeah.
So I'm taking the minified version of Three.js. It's 400 KB.
Yeah.
Is there a way to bootstrap wherever it just needs and just load that?
Okay, so the question was, is there a way to get a more customized version of Three.js? Because minified, it's 400K. Unminified, it's about 800, actually, yeah. So that's a good question. I mean, people tend to ship minified stuff with this. If that's still too big, there's a whole build system that comes with the sources. So the minified one is the result of whatever the latest build is through his process. But you could totally, I mean, there's a minimum set that's much smaller than that. You could customize that, but you'd have to get into his build scripts to do it, right? Or cherry pick pieces of the core and not take the rest. And when you look in there, there's also tons of extra stuff. Not just there's a subfolder of the source called extras, but then there's extra even more stuff in the example code. Some of that can be really useful because there's a lot of custom special effects. So you might really have to get into a mix and match of your own thing. And I think the biggest issue with that is ongoing support and how you deal with it. You know, if you do you fork the repo and get into it that way, and then you know, maybe do some pull request stuff and see if he'll bring some of it back into the main line if it's generally useful. You know, I don't know, but I mean, you get everything there, including a build scripts to go with. Another question over there? Are you running the files from a web browser? Are you double-clicking to launch them? You can't do that. You have to go to localhost. Do you have a web server on your machine? Say localhost blah, blah, blah. If you double-click, you won't see the textures. Unless you hack Chrome and turn the flag on that says ignore file cross-origin, blah, blah, blah. And I don't remember the flag. If anyone knows what that is, please tell me. But again, I never use it because then I'll have this configuration that doesn't work like my customer's browser, and I'll forget that, and then I'll be chasing bugs down for a week that don't exist. Everyone got this? Figured it out? Let's go look. Did someone do it this way or a different way? On the Fong material we created, we supply a different color. RGB, 4 zeros, 2 Fs, and we have blue.
I just changed the light.
The other way you could do it, sometimes there are not, you know, there's not just one answer, there are two or more, is to change the light color. So did you change the light color to that same value? Right on. Who did it my way? Who did it his way? He tried both. You win. All right. See, pretty easy to program at this level. What do we get coming next? Let's look at the next lab. Light the cube from the top instead of the front. I kind of got into a detailed explanation of how directional lights work and the syntax and the weirdness of it with the position. What would you have to do to light the cube from the top? And then once you've done that, the results may surprise you. Sounds like you've already done it. What? You don't know if it looks right?
I mean, is that right?
Yeah. Anybody need help on that? Figuring it out? Boy, that's a little bit weird. That's lit from the top. This directional light is only lighting the faces that it's pointing at. Now, it's also, no, that's it. That's all it's going to get, to the light from the top. This is tilted toward us. What we're not seeing is the faces that are being lit from behind, right? If our camera was on the other side of the scene, we'd probably see those front faces lit, right? A little bit. But this is tilted toward us. Is that true or am I lying? Let's see. If I tweak the position, what happens? If I don't rotate the cube. No, I'm not going to see those faces. These faces are normal to the direction of the light. So how do we do it? Everyone get the answer? So we're going to position the light at 0, 0, 1, where y is up. And that will point it toward the origin. So it's pointing down. And it's lighting the top of the cube.
0, 1, 0 means maybe.
I'm sorry. I said 0, 0, 1, because I say that a lot. 0, 1, 0. Y is up. And pointing down at the origin.
So this y scale isn't inverted, right?
This y is inverted. In normal 2D graphics, our y coordinates, positive y goes down, right? All right, so what we're doing is we're putting the light up here, pointing it down there, right? So you see some of the limitations with working with just a directional light, right? It's only going to light the stuff in its path. In a typical scene, we're going to use other lights. We can use something called an ambient light, which is just kind of light being shown, like from there's a certain amount of light in this room that's not being cast from anywhere else. It's just always here, at least if the doors were open or something, right? We wouldn't be in pitch black. You can use an ambient light to sort of light things equally throughout based on a value like that. There are point light sources which sit in a place in space and cast their light out in every direction. which is a very common light to use when you're doing realistic scene lighting. What you'll do is have 2 or 3 point lights. Like you'll place one here, you'll put another one over here, sort of like this stuff happening in the room here. But these are actually even another kind of light. These are spots, right? This is a spot casting from here going onto this wall. It's got a cone of influence, and you can kind of see the circle it intersects the wall with. Three.js has all 4 of those light types, directional, ambient, point, and spot, that come out of the box. And so you'd combine those other kind of lights to light your scene more realistically. Understanding that that can have some performance implications if you use too many of them or the wrong kind, or later on we're going to see you can turn real-time shadows on in Three.js. It starts getting the simulation to be possibly a little compute bound, either in the CPU or the graphics processor. You're not going to notice the ill effects of that necessarily if you're doing desktop stuff, but when you start moving to mobile, where the hardware is a little bit more constrained, not necessarily as high performance, you start turning those things on, they might make a difference. So you need to be aware of that, but in general, you got this toolkit that helps you do all that kind of cool lighting.
Quick question.
Yeah.
So 0, 0, 0 is in the middle of the cube, or it's in the left top corner?
0, 0, 0. Did we position the cube at all? We didn't change its position, right? So when we created the cube and added it to the scene, and it was a cube of 2 width, 2 depth, and 2 height. That is created by Three.js centered at the origin. So yes, 0, 0, 0 is in the middle of the cube. Yeah. And that's the default position. And actually, yeah, you can set the cube mesh's position. The cube geometry is always built that way. It's modeled at its origin, and it's built at a certain size. But then that geometry is contained in a Three.js object called a mesh. And the mesh is just like your light or your camera or other top level or other high level entities that belong to the scene. It has a position and a rotation. And so you can change that. So if you set the cube's position, which defaults to 0, you set that to, say, 1, 0, 0. It's going to move 1 unit to the right in X, right? But we're going to play with its rotation instead. So now let's tilt the cube. Instead of it's tilting toward you right now in the example, let's change it so it tilts away from you. And pick any rotation value you want. I mean, you can use the same one and make it negative, but you're now going to work on the cube's rotation. Let's see that one in action. See, now it's tilting away. And now I restored the directional light so that it is pointing into the screen again instead of the top. Let me know when you're done. Someone else trying to tether off my iPhone? Says I got 2 connections. Who's doing that? I didn't give you the password. I've got the world's worst data plan, too. Killing me. All right, we good with that? We ready? Here's how we do it. Everyone good? Here we go. Give up the ghost here. So the value we need to mess with is the cube's rotation about its x-axis. Remember, x is the horizontal axis? So we started out by having it tilted toward us. So we just need to tilt it back. So yeah, easiest way to do that is just negate the rotation. So the positive rotation about x happens to be forward. And this is just kind of getting your coordinate system straight. Your positive x is going this way. So that way. So positive rotation about it's going to be toward you. And negative one's going to be away. Takes a little while to get used to those orientations and really work with them. But good news is this syntax is incredibly easy. Mr. Doob has made it really easy to mess with these kind of properties in a very simple way. We're winding up to the summary of this stuff here. And so that's why a lot of people use Three.js to learn how to program in WebGL. It's a great way to get started. And it's got a lot of mileage. I mean, you can get to a pretty sophisticated level before you start hitting a wall with the features you need to do an app. So yeah, and the value it provides over that raw WebGL layer is significant. And so unless you're an engine developer who really wants to tweak out every pixel, every bit of performance and get control over every pixel, you're probably going to want to work at this level. The next section is just diving into more details of Three.js so that we're sort of armed with the other techniques we need to build something this afternoon. So I'm going to keep going on it. Do we need another short break, or are we okay? Because we got hour plus to lunch. We good? Keep going? All right. Good point to pause, though. Questions or comments before we get into the next one? All good? No one struggling? I mean, pace is good still? Okay. So, life does not just consist of cubes. I think it's time to get going on a little bit more advanced stuff. When you do get the Three.js sources, you can go into the examples and see the different kind of geometry types supported in the WebGL renderer and in Three.js in general. Actually, they're supported in all versions of Three.js. This is just the version that renders in WebGL. So we've got spheres, icosahedra, dodecahedra. What's this one called again? Tetrahedron. Cylinders, which can be turned into cones just by changing the radius of the top or bottom one. If you make the radius the same, you have a cylinder. Flat disks and circular shapes. So these are 2D polygon shapes, but they're still in 3D, so you can spin them around and do what you want with them. We got our cubes. We've got our flat surfaces. So if you wanted to, for example, make a 6-sided cube that had different textures, one way to do that is to build a 6-sided cube out of 6 of these and put a texture map that's different on each one. That's one way to do it. Toruses, lathed out shapes. I don't even know what that's called in the library. An extrusion where you basically take a path, a curved path, and a shape that's extruded along that path, and the geometry is generated for you. The library will do, and little helpers, arrows, so you can put little 3D coordinate systems in your application and show people what to do. These little helper objects in there. And Three.js generates all that stuff for you. So some of this is just going to be surveyed. Take a tour of what's in there, and I can show you some of these live. This one's great. So let's say you had map data for all the polygon stuff in the United States or your favorite country. You could take 2D polygonal data and create Three.js shapes and tweak a couple extrusion parameters. It'll not only create the 3D geometry for you, but it'll extrude it. It'll make it thick for you, or it can make flat ones for you. Let's go look at this example right now. So, but it's starting with 2D data. So you can imagine an SVG engine, going through and reading an SVG file and generating these shapes, for example, or just getting polygon data from a map service, build a little 3D virtual city where you extrude up based on height. So let's go look at that. So I've got the examples running here. Now we're just actually touring through. Is it this one? No. Oh, wait, hold on. What's it called? WebGL geometry shapes. Wasn't that it? Oh, no, extrude shapes, sorry. That one. All right? So same shape data. It's used to create lines that are drawn on the screen, flat shapes that are drawn on the screen, extruded shapes. It's a beautiful thing. So when you get some luxury of time and you want to study up on this stuff, that's pretty fascinating. Again, it's a great way to get lots of 3D data sources that are already out there. I mean, 2D data sources that are already out there turned into 3D objects in a scene for you. Like, great if you're doing city data and things like that. Oh, and this one's great, extruded splines. So spline is a mathematical curve, which can be in 2D or 3D space. You give it several points and a mathematical function to interpolate in the intermediate points between the data points. And you can make really nice curves with that. And you can not only take those curves and just draw them as lines, but you can actually then take a polygon shape and run it along that curve, and it will follow that curve. Three.js will generate this geometry for you and turn it into one of these wonderful shapes. Let me find a, I don't like the granny knot. What do I like here? Nah, it's too trippy. Torus knot. Yeah, that's pretty cool. Really nice 3D shape. And you know what? For fun, in this demo, they put in something that has the camera just follow the edge of it. Isn't that cool? Yeah. So, remember we can create a Three.js camera. We can change its position and orientation every frame during animation. So, through the magic of math, again, what's happening here is the curve is being followed. The code in Three.js that creates the curve objects for you can compute a point on that curve given where you are along the arc length. It can not only compute that point, it could find a tangent to the point based on the mathematical description of the curve. That tangent is then used to create a coordinate frame that follows the spine of this spline. So the camera is always following and oriented correctly along it. I mean, we're not just moving the position of this camera. You see how it's orienting? It's, right? That's being computed every frame through programmatic animation technique, which is just always keeping us oriented on there. Isn't that beautiful? All right, well, at the heart of all this, there's a base class called Three.geometry, which, if you guys aren't comfortable with this, please somebody tell me, but they use in Three.js a pretty standard subclassing technique, right? So circle geometry is a subclass of geometry because we're calling the base class function here, right? This is simulating classes in JavaScript. Everybody knows this stuff, right? Okay. So this is literally the code that creates a circle in Three.js, because that's a built-in type, but it's all based on a generic geometry class which has a pile of vertices, a pile of texture coordinates, a pile of normals, and the other things we need to render it, right? So in this case, this looks like the code to generate the UVs. Where's the code to add vertices and texture coordinates? You know, there's not enough detail on the slide. I'm going to pull up the actual code. Source, extras, geometry, circle geometry, bonk. Should I make the text, can I make the text bigger on here? I don't know how to do that in Eclipse. All right, well, here we go. So you pass it a radius to say how big the circle is, and then figure some stuff out. It's going to create an array of texture coordinates, UVs by convention. You're asking about S and T earlier, UV. These are the 2D coordinates into the texture. Well, the origin of, okay, so imagine a texture image, right? Rectangular image, bitmap, right? And so for each triangle, we're going to compute, okay, step back one more. A circle is actually just a fan of triangles. Can we picture that? A pie, right, of 3D triangles. And if you make enough of them, you're not going to notice that the edges of that circle are actually linear, right? So it's a triangular segment, and if you make enough of them in a fan of triangles and organized like this, you're going to have something that looks like a circle. So I'm going to basically say, by default, there's 8 segments, but you can pass in a lot more, and we need at least 3 to make a circle fan. So you could say 100 in there and get a really nicely tessellated, triangulated circle with lots of triangles in it. So this code's going to generate the triangles. And so for each one, we need to compute texture coordinates, which, well, the texture coordinate for a circle at each vertex, each triangle is going to have one vertex at the center, right? They're all fanning out from the center. So the origin is smack in the center here, right? Sorry, wrong thing. This. That's why it's 0.5, 0.5. Center is actually going to be the vertex position, which is at the origin. All right, so we're going to put that in there in a list of vertices. We're going to put that center texture coordinate in a list of texture coordinates. And now we're going to go through a loop for each segment and create triangles and put the texture coordinates and vertex coordinates in there. So we're going to create a vertex. What happens with it? We add it. Vertex. Here we go. So we start with a vertex at the origin, but we're going to change its x and y properties based on trigonometry, right? So we're creating a triangle that's There's always one vertex that's the center, and then there's two unique ones. There's this guy up here and then this guy up here. That's the first triangle. Then there's this guy up here and this guy up here for the second triangle. Maybe a drawing would be helpful, and I don't have one handy. The end result of this is we've got the list of vertices that represent the center, followed by all the ones around the outside of the perimeter. That's in our array. Same for the UVs. We start with the center of the texture map, and then we're going to generate something that you've got a rectangular texture map. We're going to cut a circular hole and slice into it and use just those pixels. Right? And then we need a normal. What's a normal? A normal is used in shading. It defines a vertex, a direction for each face. Each triangular face is going to have a direction pointing out at it. And for complicated meshes, they can be really arbitrary, and what they're going to define is how the thing is shaded. If you use a Phong shader, you're going to get shading out of this normal. Well, this is a flat shape. The normal is always pointing out. So it is 0, 0, 1. It's pointing out in Z. And what that says is light this flat. So if a directional light's coming from 0, 0, 1 and pointing at the origin, and the circle's pointing at the origin, you're going to see it head on, right? And as the circle's rotating, that normal is rotating with it. Now you've got a vector pointing this way, the light vector pointing this way, and the magic of the Phong shader is it figures that angle out, and the farther away that angle is, we saw what happened when it got all the way to completely parallel with the light ray. In the case of the cube lit from the top, it will disappear, right? As you get this way, you'll see shading along the triangle. And that's the vertex shaders using those normal values to figure that out. So that's what all that magic's about. And for a lot of your applications, you wouldn't even bother with all this stuff, but this is the thing that creates a circle inside Three.js that everybody can use. So it's got to work, and it's got to work with all the lighting that you use. So we go through all this complexity. The end result of it is a fan of geometry and properly textured and shaded for us. But we could make any kind of thing we want out of this. We could make the rings of Saturn, lots of things out of it. So this is how you dock into Three.js to build custom geometry. We've talked about this a little bit, but let's get to the next level of it. So we know how transforms work now. There's a matrix underneath that all the vertex values are multiplied by, so it shows up in the right place on the screen. But it's not just about moving a single object. We may want to create a hierarchy of objects. Let's say we want to make a solar system, where in that solar system we have planets. Those planets revolve around the sun. They also rotate in their own positions. Around those planets orbit satellites. Those satellites revolve around their parent planets, but they also have their own rotations about their own axes. As the planets move around the solar system, you'd expect their satellites to move with them. Now, you could write all this code by hand to keep track of everything and multiply all that stuff together yourself in terms of matrices every frame as you're animating your little solar system. Or you could just set up the right set of transforms and right set of parent-child relationships, and everything will happen for you. And that's what this example is about. And that, by the way, is called a scene graph. That hierarchy of objects is called a scene graph. And that hierarchy of transformations that are inherited is known as a transformation hierarchy. Right? So object 3D, which we saw, a light, a camera, and a mesh are all actually subclasses of, is the main unit of the scene graph that you put into your Three.js. So let's actually look at the sample and then the code that goes with it. So this is about getting into, do I have this one? Maybe I have a bookmark for this. Nope, hold on. So now we're starting to get into the following, which is I want to build an app of some complexity here with multiple objects doing the right things. So what we're seeing is a cube rotating about its own axis, y-axis, a sphere doing its own rotation. And you notice the sphere has got a cone moving around it, right? That cone is a satellite in that example I was using before, right? As the sphere would move, so moves the cone, right? And so now I'm actually just dragging with my mouse, and my mouse handling code in there is saying, change the rotation of the scene. Well, you notice you change the rotation of the Three.js scene, everything goes with it, right? And I just got some real poor man's UI in here because I didn't want to use anything too complicated. A simple old jQuery slider somewhere. And this is changing scale. And it's changing it on the whole scene. You notice every object gets scaled down with it. But that's one scale change in the code. It's not three. Okay? So let's look at it. Let's just do this in here. So we create our scene, put that camera in, usual stuff. We're going to create a group, which is just another 3.object 3D that's going to contain other 3.object 3Ds. Think of this as a div. It's like a div. It's a container for other items. Okay. Then we're going to make a cube mesh. We give it some rotational parameters from our previous examples. And we add that to our cube group. But we're not done. That cube group is also going to hold a sphere as a child of it. You notice that? We add a sphere group we're creating as a child of the cube group. Well, what's in the sphere group? Another mesh we're going to create with sphere geometry, another material. Add that to the sphere group, which itself is a child of the cube group in this hierarchy. Then finally, we're going to create, well, this is the interesting part. You use cylinder geometry to create cones. The magic there is the top radius is 0. So that's top radius, bottom radius. So you've got a cone. You use the same object to create a cylinder just by making the radii the same top and bottom. Another mesh, we add that to the sphere group. So that's a child of the sphere group. And what we're seeing that, whoops, hold on, sorry. In this, because as the sphere rotates, you notice that this cone is rotating around it, right? So this is how we make, this is how you'd make your orrery if you're doing a science project for the solar system. That's pretty much, that's the principle. This is how you want to make a robot. You want to make a simple little robot with cylinder arms or whatever, right? What you do is, you'd have a main robot body, then you'd have the trunk, and the bottom part is and the head and the arms. I mean, each one of those would be parented in the right way. So your trunk would have the arms as children, an arm would have this and that as children of it, and a hand. And what would happen is as your arm moves, all the segments move with it. Then you can have this piece rotate on its own. You put that all together, and you've got a walk cycle for a human being, at least, or not a human being so much as a toy robot. We do humans differently, and we're going to explore that later. So let's do a couple of labs, or maybe I think I held them off till the end. Let me see. Nope, we got lab time here. So we're going to make some changes to the transformation hierarchy. So take that code from Three.js scene, change one line of code, and make the cone part of the cube's hierarchy instead of the spheres, and then see what happens. So right now the cube is a child of the sphere. I'm sorry, the cone is a child of the sphere. Make it a child of the cube instead. And again, this should be somewhat familiar. This is just like DOM hierarchy stuff in its concept, though in details it's different. Yes, sir?
Can you integrate physics into the scene graph?
You can integrate physics into the scene graph via external JavaScript libraries, and there's several of them. You can use 2D physics on your 3D scene using Box2D, very popular library that they've got a JavaScript port of. There are a couple of good JavaScript 3D physics libraries, Ammo, which is a port of Bullet, which was a native C++ physics library, open source. They used that mscripting thing I was talking about to convert the C++ code to JavaScript, really gnarly looking, undebuggable JavaScript. But if you can just treat it like a black box, and it's a small library. It's not like that Unreal Engine where I was saying it's like megabytes of code to download. I mean, it's tiny, right? You get some pretty high performance physics in there. And as long as you treat it like a black box, and and I think they've documented how you talk to it and all that, you can get it to simulate your physics for you. And you take the output of that physics simulation every frame and feed it to the objects in your Three.js scene graph. There's nothing built into Three.js that does it, long story short. But you'd certainly want that. I mean, take that and bounce the balls in there as they're moving around. That's a physics problem, right?
Or use real gravity for the orbit.
Or use, that would be fun. I mean, you could use gravity to actually simulate the orbits. And then something for a simple solar system sim, I mean, there's not that many objects, probably perform pretty well. Please build that and share it with everybody. That would be awesome. No, I mean, not today, but I'm saying that would be an awesome exercise to follow up. Done. I already have that. OK, so do we figure out how to do that? Let's see what it looks like. No. OK, you see that the cone is no longer orbiting the sphere. we see that as we rotate the scene, the cone still rotates with it because it's a child of the cube group, which is a child of the scene. Well, actually, what's the code? Is the code rotating the cube group or the scene? Let's see. Here we go. Yeah, so cube group. It's not the scene itself, but the cube group's rotating. So, and the sphere and the cone are both children of it, so it does the right thing. So what's that code look like? Who's got the answer? Who wants to volunteer that?
Cube group add.
Say it again?
When you add the cone, the cube group add.
Okay, actually I got it here. Let me do. Let's see if you are correct. CubeGroup.add, cone. Yes, it used to say spheregroup.add, I think. You got it. It's that simple. Next lab. Now, you know what? We want the cone to be a top-level object. How do we do that? And so now next time when we drag it, it shouldn't scale up. When we look at this example, it's going to scale up with the scene. All right, see how the cone gets bigger as well as everything else? So, and that's because we're scaling the cube group. How do we do that so that it's just a top-level object instead? See that too? I'm rotating the scene. Cone's not moving anymore. Scaling things up, down. Cone's living on its own. It doesn't want anything to do with those other people anymore. How did we do that? Let me know when you have the answer. Good enough for me. Let's look. Now we just add it to the scene. Now anything that we change in the cube group, which is what's being changed as we're using the sliders and dragging the mouse, doesn't affect the cone. Well, that's pretty easy, and that's it's just like using divs. It's just like DOM elements, just the syntax and details are all different. But that's kind of amazing. So we could build our little robot man, apply a scale to it. The whole robot's going to scale. You can move him through space. The whole robot's going to move, right? But individual rotations are only going to affect themselves and any children of that.
After the first exercise, the cone was next to the cube, but it wasn't rotating or wasn't orbiting around the cube. Why is that? No.
Let's see.
You know what I mean?
So this one,
Yeah.
oh, it's not orbiting around the cube?
Right.
Because the cube orbit, let's go look at that. That's a great question. So we notice the cube's spinning, and the cone is a child of the cube group.
Right.
Right. Because let's go look at this. What we're actually seeing here in this example. When we animate, we're not changing the cube group's rotation. We're changing the cube, which is another mesh. The cube group is a child of the cube. So we're rotating the cube in place, and the rotation of the cube group is only affecting that group and any of its children. So there's actually an extra level of hierarchy here. So the cube mesh itself can have a rotation on it. Three.js objects, anything that is a subclass and inherited from object 3D, can have these rotations on them. And that's not just the groups, but it's meshes, lights, cameras. So you don't have to even put a containing group around something if you want to make it rotate or scale.
The sphere, we rotated the whole group.
Yeah.
But in the sphere case, we rotated the whole group.
And because it was a sphere, it didn't look like the sphere
Well,
Like the cone was rotating.
yeah, you can still see it though. Look, it's rotating.
Yeah.
You can see it because of the texture map on there. Yeah, you probably just didn't notice. But oh, it's really astute observation. You got that right, and that's why, because there's an extra level of complexity here. We're spinning that cube mesh in place. Cube is a mesh, which is an object 3D. Which some people have complained about that in the design of Three.js and said there's too many ways to do that. Like, which one should I use? But it's sort of like I can change the position on a div, or I can change position to paragraph elements in CSS using craziness. It's a similar idea. You know, you've got an extra level of control there. So one man's meat, another man's poison, and so on. Let's see how much time we got. I think we got time to get through this whole section, which is a very long one about all the different graphics you can do in Three.js. And if anybody needs a breather or just a quick leg stretch, just tell me. Otherwise, I'm just going to plow forward. A break would be awesome. Can we do a 5-minute break and bio break and not leave the building and all that? Okay, come back. 12:01.